Then let's go for Rate-Distortion.
Yeah, thanks, Marius. Thanks for the organizing. I'm here. I'm going to talk about Rate-Distortion for mixed states. It's a joint work with full-type polygon and in Waterloo. So since my talk is the second last talk from the talk of the show, I learned that just to keep it very simple. So I'm not going to talk very complicated and like I'm not going to present very complicated formulas, hopefully. So even though that everybody is familiar with Shannon theory here, I decided just to give it a bit of background so that I put our work in the context. Schumacher compression basically is the quantum version of the Shannon compression problem. Schumacher extended Shannon's work by defining the quantum source as an ensemble of pure states. And he considered the compression path, assuming that there is a source that emits NIIT copies of copies from the same ensemble. And he assumed that okay, we feed this sequence of quantum states to an encoder, and we map it to another system. Let's call it an N, and then we send this N, the compressed information to a decoder. And the decoder wants to reconstruct the information as close as to the original sequence as possible. And the goal here is to minimize the dimensional system here. And the figure of merit that Schumacher considered for the reconstruction of the data was this average fidelity of 1 minus average fidelity. And basically, he showed that the optimal compression rate, which is defined as the local dimension of n over n, is equal to the von Neumann entropy. There is another model that Schumacher considered in the paper, and he defined it as a purified source, but I'm not going to talk about that one here. Okay, it's just a bit of overview. There is something about this error criteria actually. When we compare the whole sequence of input data with the output data, which is called the block error, there is a phenomenon happens here. So if we just compress just even a little bit below the optimal compression rate, which is the von Neumann entropy, there is a strong converse property, meaning that the error suddenly jumps to 1, which means that you cannot go below the von Neumann entropy at all. So this for the quantum source was proven first by Josa and Schumacher, assuming that the decoder is just the unitary, and later it was fully proven by Winter, assuming that the decoder is any general simplicity map. Okay, so what if we do just a little bit of like looser error criteria instead of like comparing the whole blocks of input and output data? Let's just compare everything locally, meaning that I compare the output sequence, the first one with the first input, the second with the second, and so on. And this is called the local error criteria, and it has been already studied a lot in the context of classical information theory. And this kind of looser error criteria allows us to have a trade-off between the compression rate and error, rather than sudden jump if we go below the rate of the compression. And this is called the Rate-Distortion problem, which basically is like you're getting you can compress the source more in the expense of having bigger errors. Okay. So I thought that I'm going to talk about mixed state. Let's just review some mixed state data compression as well. So the definition of mixed state compression was first considered by Koashi and Imoto, and by blind here is that we have the source as the ensemble of this mixed state, and if the encoder can see this x here, the variable, it's called the visible version. If the source doesn't see it, it's called the blind version. So the blind version was studied by Koashi and it was shown that the optimal compression rate is equal to the von Neumann entropy of two subsystems in the Koashi decomposition. And when the encoder can see the index of the signal, then this problem was first studied by Rodesky, and he characterized the optimal rate, and later Hayashi showed that that optimal rate is actually can be expressed in terms of the entanglement of purification, like regularized version. Actually, this is just a regularized version. And also for mixed state, the strong converse property like was not studied before. So last year I tried to study a little bit like what happens in the case of visible and blind compression. If you want to like know if there's a strong converse property or not. So okay, this is the model that I'm review, right? This is our model. So let's assume that we have an ensemble of mixed states. And let's just write this ensemble of mixed states as a classical quantum state, meaning that I define this extra register X, which just stores the variable X of the ensemble. And this kind of representation is very useful because we can just write a simple line to show that this average fidelity is equal to the fidelity for this classical quantum state for the input and output state. And this is very useful, I think, in quantum information theory because you are somehow making the role of the reference system, which is the X, very explicit. Like so in classical information theory, maybe this is not that necessary because you can copy everything anyways. But in quantum information, it's very good to keep track of the reference system, and somehow like it's very implicit. So okay, the other thing that we consider in our model is that we consider both blind and visible scenarios in a single model by defining an extra register. So let's say that we have our ensemble source, we define some extra register that C that the encoder has access to, and if this C is equal to like if this is just an orthonormal basis such that the encoder can see the index of the state, it's called visible. And it's just a trivial, it's going to be the blind version. So this is our setup, which is like very similar to what like data compression setups. And we also allow registers like the encoder and the decoder share kind. So, okay. I said that we are going to consider local error just to have trade-off between the rate and distortion. And we consider a general function as a distortion. A simple example would be just a fidelity, but we consider any function that you can define on a given state, and we only assume that this function is continuous and we only like impose that this function is convex just because we need it at some point to prove that some rates are continuous. Otherwise, I don't know how. And we define the rate distortion function like the minimum rate that can achieve for a given distortion. Okay, so the thing is that similar to so many other problems, when there is entanglement, everything gets much simpler. So already Sandra talked a lot about data and closures results in the morning, so I'm not going to review that one. But somehow our results are kind of an extension of that one to mixed states, and already they showed that for the entanglement assisted rate, you're going to have a single relative quantity. So it is a very similar rate to the rate of data. But the thing is that we don't have a purified source, but somehow the rate that we obtain is with respect to some purified state, but like minimize over all channels that keep the distortion for the reduced state, not the whole purified state. That's a difference. Okay, so we minimize this mutual information quantity, which is like with respect to this purified state over all such channels, such that keeps the distortion below level T. Okay, this is a single letter rate, but to talk about the multi-letter rate, it was already like in the talk of Sandra as well. We're going to need a quantity which is called the entanglement of purification. So this is already from early 2000s defined by Baghali and Khanian. So let's say that we have the bipartite stable AB. How do we define entanglement of purification? Just consider any purification rho AB and divide the purified system into two parts. Like let's call them A prime and B prime, such that if we look at the entropy of the reduced system on each of these like sections, either A prime or B prime, the entropy is minimized. This is called entanglement of purification. which appears in many quantum information processing tasks. So there, one of the important questions here would be, of course, if this quantity is additive or not, and this hasn't been known so far, but there are already some results by Chen and Hinter having some numerical simulations showing, strongly suggesting that this is not an additive quantity. Okay, so then we're gonna have like the unassisted version where we don't allow the encoder and the decoder share any entanglement. We get a very complicated formula here. It's kind of scary. But it's just entanglement and purification again with respect to the purified state, not just the mixed state. But the thing is that we have the minimization over these kind of channels, which give the distortion for the reduced state, for the mixed state, not for the whole state on the purified system. So this rate is very complicated, and probably even if we have the entanglement of purification like additive for specific set of states, then we have another problem here, because in this minimization we have like optimization over all channels, which takes system A, which is a system to be compressed, and the side information system to system B, and this is not an IID channel. This is a general channel applied at system AK and CK. So what I'm trying to say is that even if entanglement of purification is additive, probably we're going to still have problems to simplify this rates more than this. Okay, so the proof ideas, I just don't want to talk about the proofs now, but just a little bit to give some ideas. I would like just to mention that surprisingly, Schumacher and also the extension quantum state distribution is a very strong code, even for mixed states. So the thing is that we do some local pre-processings and in the encoder and the decoder side, and we show that these local pre and post processing doesn't affect the fidelity, doesn't increase the distortion. But in the end, we obtain some subsystems, we define some new systems, but we only use like Schumacher or quantum state distribution to achieve the rates. So it's still, it seems like that we don't need more than Schumacher compression or quantum state distribution to do this kind of compression, even for mixed states. So as for the converse, so in the unassisted case and both the unassisted and assisted version, we use some properties of entanglement of purification and quantum neutral information. For example, like the monotonicity to obtain the lower bounds. Probably I would say the most complicated thing here to obtain the converse is just single letterize this neutral information quantity. Otherwise, yeah, there's nothing more than that. So I just didn't want to put so much stuff about the converse. Okay. Maybe just a little bit about the rates and how we can simplify them. Okay, I said that we have two scenarios, the blind version and the visible version. So in the visible version, already for the plug error, we have entanglement of purification, which is very complicated. So about that one, okay, if we don't have the side information system, I mean, if it's blind, it is this kind of entanglement of purification formula. Basically, our paper operationally proves that in the limit of very small distortion, we going to zero, we recover the Quashy motor result. This is what our paper operationally shows, but we also do some extra calculation and basically show that this minimization of entanglement of purification over these kind of channels basically gives us the von Neumann entropy of the Quasimodo decomposition of the state. So I'm trying to say that we can just a little bit simplify this quantity, but only in the limit of t going to zero. Otherwise, we cannot. So that was why I was asking what happens like if the distortion is okay. So I already want to conclude the talk. I don't know how much time I have, but
You're not in a hurry.
yeah, okay, good. So what we did was that we tried to unify the Boolean and the visible compression model in a single model just by defining an extra register. And if this extra register stores all the information about X, the variable X of the ensemble, we retrieve the visible model, and otherwise, if it's just a system, a trivial system, it's just going to be the blind compression. So the other thing is that we didn't just consider a distortion, a given distortion operation, such as fidelity. We consider all possible distortion operators, but we impose only two things on that. One is the continuity, and the second one is the complexity, because we need these two properties to show that our rate is continuous with E. That's one point. Okay, so for the entanglement assisted case, we did a single letter formula in terms of the mutual information with respect to the purified state still, but the optimization is done over channels that preserves the distortion only for the reduced state, not the purified state. For the unassisted case, the rate is super complicated, so we only could simplify it just a little bit in the limit of very small distortion, P going to 0. There's also something else that I didn't talk here because like the rate region was super complicated, was the full rate region. When we consider trade-off between entanglement and between the entanglement rate and quantum rate, we fully characterize the trade-off between these two rates, which is in the paper on archive. So I would say here, actually, probably the biggest question here is still not related to this, to our problem, but it's like additivity of the rates, which usually boils down to already understanding other quantities, such as entanglement or purification in this case. So there are already suggestions that this entanglement or purification is not additive, so probably we are not going to get additive rate here anyways, but we have another hurdle, which is optimizing over channels, which is not our tensor products form. So that's another problem. So yeah, of course, like it would be super interesting to be able to show that entanglement purification is additive, because it's gonna additive or non-additive, which is like it's been suggested that it's not additive. At least we are gonna get this idea that we cannot simplify the rates anyway. So by that, I would like to conclude my talk. Sorry, I just want to talk very shortly. And thanks for listening.
Plenty of time for questions.
In the unification model, when the C system is non-orthogonal signals, is there an operational interpretation for that? Where you kind of like, you have some partial information about the signals, but you can't really distinguish.
Yeah. Well, it's just a general side information system. It's like a state splitting somehow. Yeah. But it's like state splitting, but with local error criteria. But the state splitting is, I think it's a bit different because of course you have a purified source and the system C is quantumly entangled with system A, but here we just assume that it is classically correlated. Yeah.
Oh, I have a question for you. In your complicated formula, right?
Mm-hmm.
You only allow for these channels to have the uniform bound for every K, which you just had there, right? Right here, delta K is let's say P. Well, that doesn't change with K, right? But if you have some resource, if you were to take a tensor product and that goes also, the delta also grows, shouldn't you allow a D to the K or something like this? in this?
No, because this is just average. There is an average in the distribution. Let me bring,
Okay.
yeah. it's-
Oh, you'll do this one?
Yes.
Okay.
Yes.
Yeah, then.
So we define this delta for each copy and then take the average.
Okay, you're not taking the large one.
No.
Okay, so that's like, yeah. Good. Well, then, I would suggest we thank her again and maybe meet at 5 before so that we can stop a little, finish a little earlier. But anyway, let's thank her first.